All right, we have a 2 millimole sample of chlorine that is sealed into a 2-liter reaction vessel, heated to 1,000 degrees Kelvin to study its dissociation into atoms. So first thing I might do here is think about writing an equation. So I see that chlorine is dissociating into chlorine atoms. So that would be my equation. I have 2.0 millimoles of this and 2 liters. Temperature isn't changing, so that's just informational. And I have Kc. So that's important because that tells us this is based on molarities. So I don't need to use the temperature to find a pressure. So I could find Kp if that was given, but since Kc is given, we're going to stick with that. So I'm going to do 2.0 millimoles and 2 liters and get that 2 moles per liter. So millimoles is just like any other milliliter. There's 1,000 millimoles in 1 mole. And that is going to give me 1.0 times 10 to the negative third moles per liter. So that is my initial concentration. Okay, I have none of the chlorine atoms, so that means my equilibrium is going to shift to the right. So that means I'm going to lose diatomic chlorine, and I'm going to create 2 chlorine atoms for each one of these that splits. So at equilibrium, I'm going to have 1 times 10 to the negative third molarity minus x, and this I'm going to have 2x. So when I write my Kc expression, it's going to be chlorine atoms squared brackets because it is molarity or concentration all over diatomic chlorine. So then I'm just substituting in 1.2 times 10 to the negative 7th equals 2x squared over 1.0 times 10 to the minus third minus x. Now, we're going to simplify this one, so we're not going to do the complete quadratic equation like we did the last one. So there are 1,000 units, so negative 7 to negative third is 1,000 units, or excuse me, 10,000 units because it's 4 factors of 10. So this is small in comparison to this number. So this value is going to be tiny. So we are going to eliminate this x because it's small. So we have something that has a very small Kc value, so that means there's not a lot of product being formed. So I can't eliminate this x because I'm starting with 0. So the amount in terms of 0 is not insignificant. So that is going to give me, when I simplify this, 1.2 times 10 to the negative 7th over 4x squared equals 1.0 times 10 to the negative third. So I'm going to cross multiply and simplify. So I'm going to get 1.2 times 10 to the negative 10th equals 4x squared. I'm going to get x squared is equal to 3.0 times 10 to the negative 9th. And then I'm going to take the square root of that, and x is going to be 5.5 times 10 to the minus 6th. So again, you can see that is really small. I'm sorry, 10 to the negative 5th. Okay. So to find out how much chlorine I have, I'm going to substitute this back in. So I'm going to have 2 times 5.5 times 10 to the negative 5th. So this would be the concentration of the elemental or atomic level chlorine. And then I'm going to do 1.0 times 10 to the minus 3 minus 5.5 times 10 to the negative 5th. And that is going to give us rounded off 9.9 times 10 to the negative fourth molarity. Now, the question that we need to answer comes back up to what percent decomposes. And there's a couple ways to do this. The easiest way, I think, is to look at this. So this is how much I have remaining as chlorine. So I'm going to do my 2.0 liters and come back to millimoles. Okay, and I just wanted to make sure that you get the idea of always using molarity. Oops, missed my 1,000. So this is 1.98 millimoles. So that's how much remains. So you have a couple ways to do this, but if I do 2.0, this would actually round to 2.0, but I'm keeping an extra digit just so I have something to look at here. This would be 0.02 millimoles has decomposed or dissociated. And if I do that over my original 2 moles, so 0.02 divided by 2 times 100 is basically 1% dissociates. So you can see that a 1% dissociation gives us a very low Kc value.